I'm starting recording accordingly. So the topic of today's lecture is labeling using heavy halogens. Still, I would like to start with something else. And reason is that our primary goal at Oncotheranostic Centrum is to develop radio-labeled peptides and proteins. So first and foremost, the applicability of labeling method for labeling of protein and peptides would be a red line in today's lecture. And I would like to start with a brief reminder of what proteins and peptides are and their critical features, which are essential for us. Okay. So generally speaking, we could use the terms polypeptide with about both proteins and peptides. There is no strict definition or consensus definition what is peptide, what is a protein. Some people say that peptide is everything which is smaller than 10 kilodalton. Some people say that peptide shouldn't have tertiary structure, but for us, very often we use term peptide if it's possible to produce this compound using chemical peptide synthesis. Very simple, but they have a general feature. So they are biopolymers which consist of amino acids joined head-to-head by peptide bonds. And in nature, the same 20 amino acids occur in all protein. There is one more, selenocysteine, which can be in principle encoded, but this is an exotics. Still, those 20 amino acids perform well by exposing variety of function. They might be basic or carry positive charge, such as, for example, of lysine or arginine. They might carry negative charge and have acidic functions, such as glutamate or aspartate, might be uncharged bipolar, and example are tyrosine here or serine, or they might be quite heavily lipophilic, such as, for example, phenylalanine. And Mother Nature uses them a tool to exercise a variety of functions. So proteins are really constituent of the body, participating in creating a part of structure, exercising a variety of enzymatic function, participating in immune response or in signaling. For exercising certain function, structure is important. And the simplest way to organize in loops proteins is to form disulfide bond by 2-histidine by oxidation forming the disulfide bridge, which enables to fold the polypeptide chain. Another important feature is the property of peptide bond, which is rigid and which is polar. And thanks to this property, some polypeptide could fold in variety of structure. For example, alpha helix or beta sheet. And we could find those structure in a variety of different proteins. For example, here is a structure of IgG antibody, and it consists from a number of beta sheets which are folded additionally using disulfide bond. And this is working tool in a variety of targeted treatments. So why should we label them? First and foremost, currently monoclonal antibody are created to recognize a variety of tumor-specific antigens. They are used routinely. For example, antibody targeting HER2, epidermal growth factor, vascular endothelial growth factor, and famous example, PDL1, so programmed cell death receptors, which enable to elicit an immune response in cancer tumor. In very commonly, there is a heterogeneity of expression of molecular target, and by labeling of antibody, we can in principle detect expression of target in particular patient and select an appropriate treatment. Now, another type of targeting protein has appeared, so-called scaffold proteins, and we work with this. They are much smaller than antibody, which give them attractive properties, and they could be used for imaging of molecular targets in tumors, but also for therapy. And our Centrum for Oncotheranostics mainly works with scaffold proteins. And another type of commonly used polypeptide-based radiopharmaceuticals, it's analogs of signaling peptides, which are specific to receptors which are overexpressed on the surface of tumor cells. And examples are somatostatin analogs, very famous example, bombazine analogs, cholecystokinin analogs, and variety of other peptides. So it's important branch of nuclear medicine and nuclear tumor targeting and personalized medicine, I would say. So therefore, protein and peptides is a focus of our work. And during this lecture, we are going to talk about heavy halogens. So overall, halogens belongs to 7 groups of periodic system, and they include astatine, iodine, and bromine, but also fluorine and chlorine. If we consider labeling chemistry, they differ quite a lot. Fluorine is the most electronegative element in the periodic table, and its feature in the labeling are very much different compared to other halogens. So we will not consider it today because it's completely different kind of chemistry. What concerns chlorine, there is a single isotope of chlorine which is potentially useful, and half-life is 30 minutes. It's a bit too short, so production has been reported, but I don't remember any paper which dealt with chlorination of labeled compounds for medical use. Our focus would be on bromine, iodine, and astatine, which share a number of features. They are homologues, not exactly the same in chemistry, particularly astatine, which is so heavy that it sometimes behaves as a metal. Bromine and iodine, though, are the most classical halogens, and they have a number of important features for us. First and foremost, they form stable covalent bond with carbon. That means that they do not dissociate this bond spontaneously in vivo. You might have an enzymatic system which could remove halogen from carbon, but good enzyme could do whatever you wish. So normally they are stably attached to carbon atom and accordingly to organic compounds. Labeling chemistry is very well developed. Historically, iodine 131 was the first radionuclide which has been available to research community. So researcher works from late 40s of last century with iodine. And what is important that heavy halogens isotopes have a variety of decay schemes differing in emitted radiation and half-life, and you might be able to select the most appropriate label. Here is a list of potential labels selected from heavy halogen, and you could see that you could find nuclide with potential application for PET, for single photon emission tomography, for therapy. Iodine 125 is very convenient nuclide to work in vivo. And they also offer a variety of half-lives which enables to select a label which meets your requirement, both in terms of in vivo kinetics and emitted radiation. When talking about heavy halogens, the typical one could divide the reaction in two classes. One is electrophilic halogenation or oxidative radiohalogenation, and nucleophilic. And classic variant for electrophilic halogenation is iodination of activated phenolic ring. Those who still remember organic chemistry might know that phenolic oxygen activates ortho position in phenolic ring by creating oscillating structure, and in this way creates at least partial positive charge in ortho position. So if we manage to oxidize iodine, it would be, of course, very electrophilic, quite electronegative, and it would selectively form carbon iodine bond. And in this way, you would have a label compounds. The major intrigue was to create electrophilic fluorine. So normally we get iodine from whatever sources is as an iodide, which is quite nucleophilic. So in this way, we need somehow to modify. Historically, one diluted radioiodide with iodine 2. This approach worked, but it had a number of disadvantages. First and foremost, we adding a carrier non-radioactive isotope of the same element, and since reaction does not have any selectivity, we just ruining specific activity of the labeled protein. Second, if you have iodine 2, the reaction is caused by first homolytic dissociation in the bond. So one atom will be positive, one negative, and it's not given that positive charge will be on radioactive atom. So in principle, you cannot have a yield of more than 50% in this case, because at least 50% would be occupied by stable iodine. There has been an appreciable work put into development of iodinating agent. One, for example, was, to use iodine chlor interhalogen compound, which worked appreciably better because chlorine is more electronegative than iodine, so the dissociation of bond would result most likely in negative chlorine and positive iodine. The key was development of chloramine T labeling methods in early 60s. So chloramine T is normally disinfectant and possess oxidizing property. Here is a complicated scheme of disproportionation and counter-disproportionation reaction in aqueous solution, which in the end give us oxidation of iodine. I don't want you to remember it. I don't remember it myself. What is the most important, that at least in 2 cases, you need involvement in proton in this reaction. That simply means that this reaction works reasonably well in neutral conditions, works excellent in acidic or slightly acidic condition, but would not probably work in alkaline condition. And this is one of the pitfalls in chloramine T labeling. You need to make sure that your labeling conditions are acidic. The problem is that to stabilize iodide in iodide form, one often use alkaline solution. So you need to ensure that you work in acidic condition. One issue with a chloramine tea is that it's a bit too strong oxidant, and later on a number of other oxidants have been proposed, such as chlorsuccinimide and so-called iodogen. And common feature that they generally work in aqueous solution one way or another. Well, here is an example of iodination of small molecule, which once upon a time has been done in our group. I lost the laser pointer. So this is a development of compound for radionuclide therapy using Auger electrons. This is daunorubicin, which is anti-cancer drug, and it works as DNA intercalator. So this part builds into DNA. So idea was to label it into carbohydrate part, because it's the only part of this molecule which can be modified without losing property of DNA intercalation, and deliver using liposomes to cancer cells. So we performed this reaction of labeling of activated phenolic ring in methanol. The compound was pretty lipophilic. So lipophilic solvent is good, with slightly acidification using acetic acid. And using chloramine tea, we got a reasonably good yield, 50 to 72% within 5 minutes. So, and this reflects all the features of chloramine tea labeling. Now we have problem with control. So, chloramine tea provides a quick oxidation within essentially 1 or 2 minutes. It oxidizes efficiently all halogens from bromine to astatine, and works very well both in aqueous media when we need to label protein and peptides, but also in non-aqueous, for example, methanol, and this is helpful if we want to label lipophilic small molecules. The issue with chloramine tea is that it's too strong oxidant, and it can cause oxidative damages to protein. One of the typical problem is disruption of disulfide bonds when cysteines got oxidized to sulfonic acid derivatives. So then the structure is gone, and accordingly, for example, antibody is incapable to bind to its molecular target. Very good solution is the use of iodogen. What is interesting that iodogen per se is non-water soluble. So typical operation is that one dissolves iodogen, for example, in methylene chloride or chloroform, and let put in a reaction vial and let the solution dry, natural way to create a very, very thin film of iodogen in the reaction vial. Thereafter, one could add just iodide and the protein to be labeled and incubate for 15 minutes or so. So iodide got oxidized and react with tyrosine residues, which contain activated phenolic ring. So the feature is very mild oxidation, much milder than compared to chloramine T. Works good enough with iodine and astatine, and in principle works well both in aqueous media and some non-aqueous media. For example, methanol. In methylene chloride, it will not work, of course, because it will be dissolved. One could buy now commercially available iodo beads, where small 3 millimeter glass beads are coated, pre-coated with iodogen, and so-called iodo tubes, where the tubes are also pre-coated with the iodogen film, approximately $10 a piece. Sometimes it makes sense because preparation of the iodogen film is an art and requires a lot of efforts. Somewhat slower reaction compared to chloramine T. Typically, when you label protein with chloramine T, 30 seconds might be enough. Depending on the concentration, sometimes it might be up to 2 minutes, but generally your labeling takes place. With iodogen, you need to wait up to 15 minutes, but this not too harsh time span, so it's possible to work with it. It's too mild to oxidize bromine, which is the most electronegative among heavy halogens. So we applied it for astatine, for bromine, for iodine, but it doesn't work for astatine. Well, not always it is possible to use activated phenolic ring, especially when you're working with the small molecules where hydroxy group might create undesirable features and structure properties relationship. In this case, very often one uses iododemethylation, where metal acts as a donor of electron or cause a shift of electron density to carbon atom. One could use mercury compound, one could use thallium compound. In our hands, the best way was to work with 3-alkyl-stanil derivatives, like 3-butyl-stanil or 3-methyl-stanil. And those compounds are very stable per se. Some compound has been synthesized 20 years ago, but after 20 years of storage at -20, it's still perfectly reactive and can be used in labeling chemistry. So apparently carbon is more electronegative than any metal, so it withdraws electron density to it, which results in electrophilic attack from iodine plus, creation of an intermediate compound, and then further 3-alkyl-stanil group could leave and result in organic aromatics bound firmly to halogen. So this is also one of example from our program for Auger electron treatment, where we used 2 variants with 3-methylstanil derivative attached to aromatic ring, and it might be simple benzene ring, it might be contain heteroatom which adds a little bit charge and hydrophilicity in physiologic condition. And again, we got a very, very decent yields of radioiodination in this case, over 90%. So now, markers. So which factors influencing radiohalogenation? Here is an example taken from examination work of one of our master students. He worked in this case with another type of halogen acceptor, boron cages, but the features are the same and we can follow it. So the labeling is, of course, dependent on concentration of oxidant, in this case, chloramine T. So if you have too low concentration, then nothing will happen. So iodine, iodide, or bromide would not oxidize spontaneously to electrophilic species. Even if you add too little, still nothing will happen because the just oxidized oxidant would be killed by some reducing impurities which always are present in reaction mixture. So you need to pass certain threshold, and thereafter the yield would be more or less proportional to concentration of oxidants. Then after a while it will reach a plateau when everything which has been oxidized can attack substrate and bind to it. But if you will increase further the concentration of oxidant, yield will be dropped. And the reason is that one could over-oxidize iodine to periodate or metaperiodate, which are not reactive anymore in electrophilic reaction. So generally, optimization of any radioiodination includes the evaluation of dependence of yield on cut concentration, and ideally we should find the flexion point here and then try to have our working concentration just beyond the flexion point. In this case, we should have very reproducible yield of our reaction, but we will not over-oxidize iodine and also will not over-oxidize our substrate, which is always a risk. if we look what happens with the bromine, it's somewhat different. So the shape is in a way similar. So we have sort of threshold value, proportionality area, and a plate. But since bromine is much more electronegative than iodine, you need noticeably higher concentration to oxidize bromine and trigger the reaction. Well, of course, any reaction is dependent on amount of substrate. And here is similar story. You typically have somewhere threshold amount, because if you have too little substrate, your oxidized halogen would react with something else. Then you have proportionality area and the plate. So again, we are interested in finding this flexion point, because Jawad, sorry, I'm giving a lecture. So we need to find a flexion point here. And work with a higher concentration. We are not interested to go further too much, because otherwise we use very often custom-made substrate precursor, which cost a lot of money. And finally, the time dependence. And as I mentioned, that iodination, electrophilic iodination is very rapid reaction. We have measured the yield up to 30 seconds, but we didn't measure shorter time points because inaccuracy would be too high. But even 30 seconds was enough to reach a plate. With the bromine, it's not the case, so we're reaching Plato of the yield at around 2 minutes, and to be on the safe side, we prefer to work at least with 3 to 5 minutes of reaction time. So they behave quite differently. And one and very important feature is pH dependent. As I mentioned, that action of chloramine T, and to this end all other accidents currently in use are dependent on the accessibility of free protons. So in acidic and neutral compounds they work very well. Even at PBS with pH of 7.4, there is slight decrease of labeling yield, and it goes down quite dramatically when one uses pH 8, and no point to go further with it. An alternative to electrophilic radiohalogenation is nucleophilic radiohalogenation, which might be considered more natural, as iodine is typically shipped in iodide form, so it's nucleophilic. And there are 3 classes of reaction which are used in nucleophilic radiohalogenation. It's substitution of alkyl sulfonates, leaving group, halogen exchange or isotope exchange. Essentially, here the mechanism is very similar. So, for example, alkyl sulfonate withdraw electron density from carbon to oxygen and creating opportunity for nucleophilic attack. And then the bond is, after intermediate compound is disrupted, and we get iodinated compounds. Very typical leaving group, depending on what you have here. It might be triflate, tosylate, or methylate. So that are typical precursor for such reaction. Here is one example of such reaction where iodination by substitution of alkyl sulfonate has been performed for glutamate channel blocking agent. Yield was not bad, 83%, but I would draw your attention to reaction conditions. So it was 180 degrees centigrade. So essentially, typical reaction media is either malted acetamide or one place iodide and substrate in inert atmosphere, evaporate to dryness, and run it in a solid state. Well, not every organic compound would tolerate such a heating. So it's pretty tough condition, and even in these conditions, the reaction would be accomplished to a reasonable degree after quite a while. So one can say that the substitution of alkyl sulfonate might have disadvantages of relatively long time and high temperature, which are required for this. Good feature is that, of course, the precursor and label compound are different. So in this case, you could find the appropriate chromatographic technique or solid phase extraction, which would enable you to separate precursor from label compound, and in this way reach a reasonably high specific activity of your label compound. Another example is halogen exchange reaction. In this case, very typically to iodinate something, one put bromine as a leaving group. Mechanism is the same. So electronegative halogen withdraw electron density from carbon, creating a precondition to nucleophilic attack. And not very rapid reaction. You could see temperature over 100 degrees, but it takes 2 hours to reach a yield of 60 to 70%. Separation of two different halogen compound might be a bit more tricky compared with separation of halogen compound and alkyl sulfonate, but still possible, and one could purify the precursor from label compound and get a final compound in pretty high specific activity. So in this case, Again, high specific activities, positive feature of this labeling approach, but disadvantage long time and high temperatures. Well, strictly speaking, halogen exchange or isotope exchange is a subtype of the halogen exchange because, for example, if you want to iodinate something, you could use cold iodinated precursor for this reaction. And to the best of my knowledge, this is a way which is used in Tomsk for labeling of fatty acids or labeling of methylbenzyl guanidine. Still, disadvantages are the same. Long time, often high temperature, and if you want to speed up this reaction, you need to rise the temperature appreciably. Problem is that since you have here iodinated compound as a precursor and you have iodinated product, you cannot separate them. And reaction actually is dependent on amount of the substrate and ratio between substrate and radionuclide. So you can forget about high specific activity in this case, never works. And to compare, this is example taken from paper of Len Wiebe from early 80s. So he used for the same reaction the isotopic exchange or chloramine T. Probably 30 minutes, it was an overkill in this case, but anyhow, within 30 minutes, he reached better yield using electrophilic reaction than in the case of halogen or isotope exchange. So this is definitely cannot be used for labeling of protein or peptides. I would never dare to expose peptide to temperature of 180 degrees for a couple of hours. And high specific activity of labeled product it cannot be obtained. So this is a labeling approach which is limited to compounds which are anyhow abundant in the blood. For example, for fatty acids, as it is used in Tomsk, it's perfect. We have plenty of fatty acids in our blood, so what? We're adding a little bit. So it will work as good for myocardium study as high specific activity. But it's a particular application for that, and it cannot be used for other methodology. So we could conclude that long reaction time, elevated temperature, low specific activity, limit application of this type of radiohalogenation to a few cases when, for example, substrate is sensitive to oxidation and specific activity doesn't play any reasonable role. But they cannot be applied for labeling of proteins or peptides. So now we switching to labeling of proteins and peptides. My question is, do we need 5 minutes break or to move a little? We are going for nearly 50 minutes. Ну, давайте, что, 5-10 минут. Ну, хорошо, давайте тогда 5 минут просто, чтобы подвигаться. Так? Хорошо, спасибо. Okay. Bye. У нас есть немножко еще времени. Мария, как вы оцениваете уровень презентации? У меня есть проблемы, потому что я не очень понимаю уровень аудитории. и поэтому склонен к достаточно простеньким объяснениям. Я прав или я не прав?
Все понятно. Самое основное, самая суть. Презентации не перегружены, плюс вы еще объясняете дополнительно по каждому слайду.
Окей.
И это все усваивается понемножку.
Хорошо. Ладно, но это всегда проблема. У нас, к сожалению, на нашем магистерском курсе примерно та же самая ситуация, то есть очень разноплановый бэкграунд у людей, поэтому приходится более простым объяснением тяготеть, иначе потеряю половину аудитории. Ну ладно, хорошо. То есть оно не выглядит чересчур примитивно и достаточно информативно, да?
Да, легко усваивается материал.
Ну хорошо. То есть это, в общем, основные и базовые вещи, которые нам нужно понимать, когда мы занимаемся мечтой. Как это работает, какие факторы влияют, чего нельзя делать. Без этого не обойдешься. Ну ладно, хорошо. Тогда можно будет продолжать. Не очень послушный у меня. Поинтер. Так, у меня вопрос. Все вернулись с перерыва. Можно устроить легкую перекличку? Кто на месте?
Да, можно.
All right. Then we continue with our lecture, and we coming directly to labeling of protein and peptides. Fortunately, majority of proteins and many peptides contain amino acid tyrosine, which has an activated phenolic ring. So we can use this reaction, direct electrophilic iodination, for those peptides. So we using chloramine T or iodogen, we can work at in aqueous solution, we can work at neutral pH, and that means that majority proteins which are useful in vivo would be stable and tolerate this reaction. And typically we mix in phosphate buffer pH 7 or 7.4, the protein, the iodide, and adding chloramine T for 30 seconds or so, couple of minutes. And when we understand that the reaction is accomplished, we adding some quenching agent, such as, for example, sodium metabisulfite, which is quite potent reducing agent, and which neutralize chloramine T. Depending on quality of iodine, one could typically reach 75 up to 90+ % in this reaction. It's very simple and very rapid. Concerning simplicity, I remember the manual troubleshooting for chloramine T labeling. If you perform the reaction and you don't get any yield, please check 3 things. If you have added substrate, if you have added iodide, and if you added chloramine T. It works. In our master program, we let guys who never made a labeling perform this reaction, and always labeling takes place. High specific radioactivity can be obtained, and it works well for proteins and peptides which are not rapidly internalized. Non-internalizing probably strong expression, so more or less everything is internalized, but some of protein internalized very slow. Works perfectly. Disadvantage is that structure can be damaged by oxidation process, or you might inadvertently reduce disulfide bond and disrupt. And in this way, your binding function of your protein would be lost. Tyrosines are overexpressed on binding site of antibodies. Generally, protein-protein recognition involves some hydrophobic interaction, and tyrosines participate in it. So there is a risk that you will modify the part of an antibody CDR, complementarity determining region, and lose the capacity. Also, in some cases, iodination of tyrosine, even in shorter peptide, might be dangerous. For example, when we started to work with antibody molecules, we started with chloramine T labeling because that straight and simple way. We killed antibody molecules, and afterwards I labeled them using more than 100 different methods. Worked perfectly, but not a direct radioiodination. We should keep it in mind. On the opposite, it has been shown that for somatostatin analog tyrosine octreotide, iodination of tyrosine even increases affinity to subtype 2 somatostatin receptor. So you never know. But it's important to keep it in mind that you're modifying protein, and it might end up in something wrong. And after internalization, catabolites leak from target cells. So we have discussed it earlier when talking about radiometals. Iodotyrosine is a major radiocatabolite of this method, of protein labeled using this method. and iodotyrosine leaks from cancer cells. The same happens though in cells with cells in excretory organs, and you might even utilize this to optimize the biodistribution. It might though happen that peptide does not contain tyrosine, but every peptide, if it's not cyclic, of course, contain at least one amino group at N-terminus. Very often they also contain lysines, which means that they also have omega amino group on lysines. So in this case, one could use so-called indirect radioiodination. And the first indirect radioiodination agent is called Bolton-Hunter reagent, after name of authors who published it first in 1964. So this reagent contains activated phenolic ring, which can be radioiodinated. You can, in principle, nowadays buy it already labeled with iodine 125 in benzene solution. And it contains succinimidyl ester, and when exposed to amino group on protein and peptide, happens the substitution resulting in formation of amide peptide bond, and peptide bond is stable. So in this case, we can use it for labeling of proteins or peptides which do not contain lysine. It's much more mild. Typically, you don't expose anything with oxidant or reducing agent. Typically, lysines are less crucial for function of antibodies, so that's why if you not over-modify your antibody, so it doesn't destroy its function, and it's suitable for whatever does not contain the tyrosines. Since it's two-step process, it's never as efficient as a single step. So yield is always lower or appreciably lower comparing with with direct labeling. So 10–20% is considered a good yield for Bolton-Hunter reagent. It turns out that this reagent is prone to hydrolysis in alkaline conditions, and you need to have an alkaline conditions for labeling because you need to deprotonate amino group. So not very efficient labeling. Specific activity is typically also lower. You need to take more substrate for labeling, and if you have a short peptide, you in principle could separate unmodified peptide, but if you have an antibody, no way to separate labeled and non-labeled. So specific activity might be ruined. And retention of catabolites after internalization by cancer cells is lower in this case. It has to be noticed that all radioiodination reaction do not perform direct halogenation with phenolic ring, does not allow to perform acetination. So astatine carbon bond is unstable when it's in ortho position to hydroxy group. So for astatine, this would not work. And I speak because I know that production of astatine for therapy is considered at Tomsk Polytechnic University. Somewhat better were the agents for indirect iodination of second generation. They work very well for all radioiodine, radiobromine, and also for astatine. And they are based on iododestimulation. There were several variants where one could use 3-methyl-stanil or 3-butyl-stanil, and also in different position to carboxy group. It might be a para, it might be meta position. They work approximately the same. So 2 steps. First, in slightly acidic condition, you label this compound and then rebuffer to obtain alkaline condition to deprotonate a minor group, and halobenzoic acid would form the peptide bond with protein or peptide. And this method works quite well. I have sort of right of my computer. Work quite well, so it's I need to stop share probably and restart it. Opa. I have a problem with sharing. I will try to do something with it. So. All right. So this method shares advantages of Bolton-Hunter reagent. Labeling is mild, but yield is typically higher. Well, our best results were around 50% overall yield. It's not a shame in this case. And one important aspect is rapid excretion of catabolites, because this is often a headache. We will discuss it later. For example, we could iodinate directly DARPins, but in vivo they undergo capture in kidney and catabolized, and iodotyrosine is excreted back in the blood and undergoes deiodination. So first few hours we have a lot of iodine background. We need to wait at least 6 hours to let catabolites to be excreted or taken up with appropriate organs and tissues. In the case of using halobenzoate, The radiocatabolites excreted very rapidly through urine, and typically we have much better tumor to background ratio. Can be used for astatine. Well, yield and specific activity are still low compared to direct iodination, and catabolites, intracellular retention of catabolites is still poor. We have to come back to this cartoon. As I mentioned that radioiodination was the first method in many organic reactions, and particularly labeling with antibodies, so quite a lot of work has been done with radioiodinated antibody for around 20 years. But then finally, researchers learned how to label antibodies with radiometals. And then suddenly, the tumor uptake of radiometals was several-fold better compared to radioiodine. It was even the concept of deiodination, that enzymatic removal of iodine from intact antibody in vivo proposed, and in the 90s it was like common knowledge, though this concept was really extremely wrong. And reason is that for lower uptake is internalization of labeled antibodies after binding to tumor-associated antigen, transfer through endosomal to lysosomal compartment, and diffusion of radiocatabolites from lysosomes, first through lysosomal membrane and then through the cellular membrane. So there were quite a lot of efforts put into prevention of diffusibility of radiocatabolites. And we know that hydrophobic molecules can diffuse through membrane or small uncharged polar molecules. But if you have large polar molecules or ionic compound, it should not penetrate the cellular membrane. It's a basis of cell biology. So idea initially was to create something which cannot diffuse through the cellular membrane. Here is one of first example of so-called carbohydrate residualizing label. In this case, the tyramine, analog of tyrosine, was conjugated to tetrasaccharide. So it still contains activated phenolic ring, which then could be labeled with iodine, and then it could be as a whole conjugated to protein and peptide. And it contains a hydrophilic core which does not permit it to diffuse through cellular membrane. So this has been applied first to determine the site of catabolism of proteins in vivo, and it was shown that it provides excellent cellular retention at the same level as a radiometal. However, the coupling chemistry was far not perfect at that time, so the yield was not just low, it was lousy. It was 2, 3, 4% at the best. Specific activity was low because one tried to increase efficiency by increasing amount of protein. And it also caused some cross-linking of antibodies. So in fact, you might study not the fate of an intact antibody, but rather fate of cross-linked variant, which is not really good. An alternative was the use of linkers which carry positive charge at physiological condition. For example, instead of benzoic acid, one could use a derivative of nicotinic acid, and you could see that here is nitrogen atom, which is should carry positive charge, physiological pH, and definitely positive charge in acidic pH. So typically there was 3-alkyl stanil here group, which could be substituted with iodine, and nicotinic acid was pre-converted into succinimidyl esters, which permit the conjugation to amino group. This work has been mainly done by group of Mike Zalutsky from Duke University, North Carolina. So they managed to get a yield up to 48%, not bad at all. They have observed some improvement of retention. We didn't. We also applied this approach for labeling of antibody. We could not see improvement of retention, but that might be caused just by internalization rate of an antibody and how accessible to proteolytic enzyme this site is. Much better was guanidine derivative, which is stably positive. And though overall yield was a bit lower, then it suddenly start to work nearly as a radiometal label with a good residualizing properties and good retention of activity by cancer cell after internalization. Moreover, analog has been labeled with astatine for therapy, and it worked also with astatine. I should say it's a good work from their side, because labeling of astatine is always very tricky. But still it works. In this case, there is an improved cellular retention, definitely. Yield is lower, specific activity is lower in comparison with direct labeling, inevitably, for any conjugation method, but it was, of course, better in comparison with carbohydrate linker. It has been, should be noticed that the positively charged compounds are preferably taken up in kidneys. And it was found that radiocatabolites of positively charged linkers result in elevated renal uptake. Not too big problem for imaging, but for therapy it might be real trouble because kidney is often dose limiting organ. And in the end of today's lecture, I would like to talk a little bit about our work with polyhedral boron anions. It's an amazing class of compound which contains from 9 to 10 boron atoms, and it's inorganic, three-dimensional aromatic system, quite exotic, and it might either contain carbon heteroatom or couple of atom, or just contain only boron and hydrogen atom. In size, it resembles benzene ring. So if you take a benzene ring and start to rotate, so it would be something resembling, for example, the decaborate anion. And what is important, that they are pretty strong acids. So at physiological pH and even at pH in lysosome, they carry negative charge. So they always charged. Even more important, those compounds can be easily halogenated, including radiohalogenation. The halogen bond, boron bond is strong, is strictly speaking stronger than halogen carbon bond. So they are not toxic, especially closer structure. So closer the decaborate is as toxic as common salt. So if you will eat 100 grams, you will probably die from osmotic shock, but otherwise sodium chloride has the same toxicity. And we have found that iodinated chlordodecaborate is rapidly excreted through kidney. So there is no preferential reabsorption. So in our work, we labeled several derivatives of polyhedral boron anion. For example, here is andecaborate, the compound which contained 9 boron atom and 2 carbon atom, and it's relatively easy to modify. Using one of the carbon atoms, so we did attached benzyl isothiocyanate, which permitted us to first label boron atom and then conjugate it to protein using thiourea bond. Another compound was based on chlordodecaborate anion, and it was more tricky because there was no carbon atom to conjugate, but Professor Igor Sivayev from Moscow managed to, well, that time he was PhD student, he managed to conjugate benzyl isothiocyanate through a minor group. And this compound worked like a charm. We tested labeling of it with a bromine and with iodine at room temperature and it was very efficient, over 90% yield in the first step, and then we conjugated it to antibodies using thiourea bond, and overall yields was around 80%, which is far not bad for indirect labeling methodology. So negatively charged polyhedron boron anions have certain advantages, as improved cellular retention and overall labeling yield is comparable with direct iodination. Still, specific activity is typically lower, but of course in comparison with direct labeling. But it is, of course, much better in comparison with labeling of carbohydrate-based linkers. When we came to this step, lutetium labeling has been developed. So major motivation for working with iodine was the therapeutic application. And, well, iodine was, or still is, quite cheap radioisotope. But meanwhile, the other researchers developed lutetium label. It starts to be commonly used, and as typical in this situation, much cheaper than initially, and its emitted radiation, particularly low abundance of gamma, makes lutetium very attractive. So, and it is a residualizing label intrinsically. So for this reason, we put aside this research since we could reach the same effect with lutetium. However, nowadays there is a renewed interest in the use of astatine for radionuclide therapy. It's one of a few alpha emitters which are relatively easily available for researchers. Particularly, it's possible to produce astatine at cyclotron and Thomson. So we should probably reconsider and come back to our work with polyhedral boron anions, particularly for application for astatination. Well, summarizing, radiohalogen provide us with variety of nuclides with different half-lives and emitted radiations, which permits selection of right label for right targeting molecules. We have a variety of methods for radio labeling of organic compounds, including both electrophilic and nucleophilic. However, for labeling of protein and peptides, electrophilic methods are preferable because they require typically much lower temperature, although require presence of an oxidant very often. Still, we have methodology which permits to avoid oxidation of protein. And depending on labeling methods, we can create either residualizing or non-residualizing halogen label. And further during our course, I will show that the non-residualizing label might be of advantage in some cases when internalization of targeting protein by cancer cells is slow. This is a case actually for adapts, for DARPins, and for affibody molecules we're working with within our oncotheranostic program. So that's it for today. Do you have any questions? Everything is clear. I'm proud. Okay. So we have, I have a question. So I've been told that 11th is day off in Russia. Should we skip it in our lecturing? Well, then we skip it. So the next our meeting will be not 11th, but what is 18th of May. That's it. Это тогда все на сегодня. Я всех благодарю за внимание, если нет больше вопросов. Я бы хотел попросить Екатерину Безверхнюю и Марию Третьякову остаться со мной для короткой дискуссии. Спасибо большое за внимание.
До свидания.
Thank you.
Thanks.
До свидания, спасибо за лекцию.
Спасибо вам, что были со мной.